I have put all of the definitions of these 5 number sets that we need to know on the screen, so you should be able to see them now. I'll really quickly go through them. Natural numbers are just the counting numbers starting at 1. So 1, 2, 3, 4, 5, and so on. If we want to write it in what's called set notation, we would put little squiggly brackets on the outside. So the set of all natural numbers is 1, 2, 3, 4, 5, and so on. And the symbol for the natural numbers is n with an extra little line. And I don't know if I drew that as well as I could. So it looks something like that. So that's the natural numbers. And I'm going backwards on this because I'm going from quote unquote smallest to biggest. The integers, which have symbol z with an extra line, are the positive and negative whole numbers and 0. So notice that the natural numbers did not include 0. The integers do include 0, and they go infinitely in both directions. So -3, -2, -1, 0, 1, 2, 3, and so on, going on in both directions. So that's the integers. Rational and irrational numbers are then kind of the next step up. So rational numbers um, follow directly from integers. So the rational numbers are q with an extra line. And rational numbers are all of the numbers that take integers and represent them as fractions. So integers are rational numbers because you could just take any integer and divide it by 1. So for example, 5 is equivalent to 5 over 1, or 10 over 2, or 15 over 3, or so on. So the number 5 is a rational number. You don't have to write a rational number as a fraction. You can just write it as 5 if you wanted to. But that would be an example of a rational number. Another example of a rational number would be 2/3, because we're taking two integers and we're writing them as a fraction or division or something like that. So anytime you take two integers and write them as a fraction, that is called a rational number. An irrational number, therefore, is any number that cannot be written as a fraction of two integers. Their decimals never end and have no repeating pattern. So they might repeat for a very short period of time, but over the long run, there's no repetition. So for example, pi and e are irrational numbers. The square root of 5, the square root of 2, those are also irrational numbers, or the negatives of either of those things. Those are all irrational numbers. We sometimes have a harder time thinking of irrational numbers than rational numbers because most of them don't have special names. But there are actually more irrational numbers than rational numbers in the number world, so to speak. And then the real numbers are all of B and C put together. Since B, the rational numbers, includes integers, B and C together means everything that we've talked about. So the real numbers are basically any number that you've ever probably thought about or used in a math problem before. That's a real number. And then a bunch more after that. So real briefly, here's a picture that can kind of help you understand these things. The natural numbers, I'm going to put the extra line there. The whole numbers, we didn't talk about those, but those are the numbers, the natural numbers plus 0. The integers, the rationals, sorry, that's a terrible line. And then all of those combined with the irrational numbers, which you can write as I with an extra line, are the real numbers, which we're going to write with R with an extra line if you ever wanted to use the symbol. So this is kind of a picture that can show you where everything goes in that diagram. Sorry, I forgot to put the R with an extra line by the real numbers. So those are the definitions. Okay, number 2, name all sets of numbers to which each of the following belongs. -12 is not a natural number because it's negative. but it is an integer. It is a rational number, and it is a real number. B, the square root of 21, is irrational and real. Something cannot be rational and irrational at the same time. Those are exclusive of each other, which is shown by the fact that in this diagram that we had, there's a line that's completely separating those two things. And again, the real numbers are all of these put together. Okay, 4. 4 is a natural number, an integer, a rational number, and a real number. So while we talk about these types of things, this is important to understand that when you see a square root, it does not automatically mean irrational. For example, if I wrote the square root of 16, it's actually a natural number, a whole number, an integer, a rational number, and a real number, because the square root of 16 is actually 4. So it will oftentimes help you to rewrite the number in its simplest form to help you out. And then letter D is actually none of the above. Letter D is what we call an imaginary number. And if you want to know more about that, you can look at the video about number sets. That's optional. But we will learn more about imaginary numbers when we get to quadratics a little bit later in the year in chapter 3. Okay, problem 3. Solve each equation given the indicated number set is the domain. So that means now we're going to take what we just learned about number sets, and now we're making that the domain. Really quick, I think we've probably already learned domain and range as like words, but I want to make sure that we know them for sure. So the domain basically are all of the inputs of the function, and the range are the outputs. Okay, so the domain is the inputs and the range are the outputs. So in this case, when we're looking at x would be the inputs, or these equations only have inputs basically because there's only one variable. So when we're looking at these things, we only have certain values that we can place in for x or substitute in for x. And so in this particular case, for problem A, real numbers. So that's any number that we have used in our mathematical career, basically, except for anything with an I in it that we haven't talked about. So let's just solve this problem. So let's subtract 6 from both sides. So negative 3x equals negative 37. X equals positive 37 thirds. That is a real number, so that's a win. So x equals 37 thirds. Problem B. This has to be in the integers. So if x is not in the integers, then we're in a little bit of problems here. So let's solve by adding 21 to both sides. So for x equals 39, x equals 39 fourths. That is 9.75. 9.75 is not an integer, so that actually is not an answer. So we would say that in the integers, there's no answer. We call that the empty set. Okay, so we put 0 with a line through it to represent the empty set, or we put that set notation that I was talking about earlier with curly brackets with nothing in the middle of it. So either of these is a way to call something the empty set. Problem C. Really quickly, we're going to remind ourselves of what is called the zero product property. So the zero product property is if we have two numbers, I'll call them A and B, and we multiply them together and it equals 0. That means that A equals 0 or B equals 0 must be true. So pause the video if you need to take note of that. If you have two numbers multiplied together and they equal 0, one of those numbers has to be 0. So in this particular case, that means that either 5x plus 4 has to equal 0, or 3x minus 7 has to equal 0. One of those two things must be true. When we solve that, we get x equals negative 4 fifths, which is a rational number, so that means we can keep it, or x equals 7/3 when we add 7 and divide by 3. That's also a rational number. Therefore, both of these answers hold as true within the rational numbers. Okay, likewise in letter D, we have 3 terms that are all multiplied together and they equal 0. Therefore, either x has to equal 0 by the zero product property, x plus 5 has to equal 0 by the zero product property, or 2x minus 8 has to equal 0 by the zero product property. So when we solve this, we get x equals 0, x equals -5, and x equals 4. Our set was the non-negative integers. Since the set is the non-negative integers, that means that -5 can't work. So I only end up with x equals 0 or x equals 4 as my final answers in that problem. So analyze the following graphs, domain and range. So the domain is basically all of the x values that make this work, and the range is all of the y values that come out in the function. So if I'm looking at the domain goes from the x value of -5 to the x value of 3, and the y values go from -4 up until 6. Now notice that I put a parentheses where there's an open circle and a bracket where there is a filled in circle or a filled in point. That is because that is the way that I can write that in what we call interval notation. So interval notation has parentheses for open intervals. An open interval means that it does not include the value, and it has a bracket for what we call closed intervals. And a closed interval would be inclusive of the value. So that would be where there's a filled in circle. In problem B, the domain is from -4 to 1. -4 is a parentheses and 1 is a bracket because of the open and closed. The range is, notice it goes all the way down to -3 and goes up to 5. -3 is included in the range. 5 is not included in the range. One way that you can kind of do that, imagine that you are just kind of scanning. So in terms of scanning the x's, everything from -4 to 1 is in there. And then if I want to scan the y's, it starts working at, it starts working at -3, and then everything works up until 5. Okay, letters C and D, I'll do these a lot quicker. The domain of C is -7 to 4, and the range of C is -3 to 5. The domain of D is -6 to 6, and the range of D is -2 to 5. Notice that I always go from left to right for the domain, and I always go from bottom to top for the range. Okay, number 6, using the domain and range given, sketch any graph that supports the data. So my domain must be between -2 and 5, and my range must be between 1 and 7, which means everything has to be hit in those values. So as long as I'm between -2 and 5 and between 1 and 7, I can start anywhere I want and end anywhere I want, as long as I get down to here and up to here, and I don't go above or below that. Now, I went a little bit above, but that's because it's really hard to draw on the smartboard. So something like that would be an example. I could have drawn it as a straight line, So if I wanted, I could go from here to here. That also would be a graph that supports the data. There are lots of different ways that I can do that. This one, I have to be a little bit more careful because I cannot include -2 in the domain and I cannot include 8 in the range. So those are important distinctions that I have to have. So -2 for x must have an open circle, and 8 for y must actually not get hit. So it's probably easiest if you start at -2, 8 with an open circle, and then work your way all the way to 6 for x and -3 for y, and make that a closed circle, and then do something like that, as long as you're not getting outside of -2 to 6 and 3 to 8.